Hello everyone again. We're gonna solve the practice questions for chapter 9. Um, let's just choose another color, or did it change? Okay. So a parallel RLC circuit contains 100 ohm resistor and has the parameter values alpha, omega naught, and we need to find C, L, S1 and S2. So for a parallel RLC circuit, alpha is 1 over 2 RC, and when we substitute R and alpha, we get the value of C by rearranging this equation. So we find C to be 5 microfarads, and omega naught is the square root of 1 over LC. So squaring both sides and rearranging the equation to make L the subject of the formula, we see that L will be equal to 312.5 millihenry. So if alpha is greater than omega 0, it will be an overdamped response. If alpha is less than omega naught, it's an underdamped response. And if they are equal, it's a critical or a critically damped response. Yeah. So for our case, alpha is greater than omega naught, which makes that an overdamped response. So to find the roots, or S1 and S2 of the characteristic equation, we follow this formula and substituting our values, we get that S1 and S2 are equal to negative 400 and negative 1600. So yeah. 9.3, determine the current IR through the resistor for t greater than 0. If IL of 0 negative equals 6 amperes and VC of 0 positive equals 0 volts, the configuration of the circuit prior to t equals 0 is unknown. Okay, so we need to find the current IR for values of t greater than 0. So we can see that this configuration is a parallel RLC circuit. Omega 0 is the square root of 1 over LC, and alpha is the same as before. So we substitute the values of L, C, and R into these equations. We find that omega 0 is this value, alpha is this value, alpha is greater than alpha is greater than omega 0, so this is an overdamped response. Since it is an overdamped response, the solution will have two real roots, and these roots are S1 and S2. We substitute alpha and omega naught to find the roots, and the voltage V of the capacitor VC is going to have this form. Why are we concerned with the voltage if we were looking for the current in the resistor? It's because the current in the resistor is just the voltage across the capacitor, or it's the same as the voltage across the resistor divided by the value of the resistor. So that's just the current. So like dividing this whole function by 3, which is the resistance, gives us the current in the resistor. So we found S1 and S2 using this formula. These are these values, and we now need to find A1 and A2 for a unique solution. We're gonna do a KCL, so IR plus IL plus IC equals 0. IR is just, as I said, it's the voltage divided by the resistor, and IL plus IC is CdV by dt, right? So at t equals 0, the voltage of the capacitor is given to be 0, right? At t equals 0. So this term will cancel out, and the current at time equals 0 was given as 6 amps. So rearranging, we find that V prime at t equals 0 is this value. So that's basically Vc prime of 0. And we plug in our value at t equals 0 into the equation, into this equation, so that we can find A1 or A2. So it's going to be 0 equals A1 e to the 0, which is 1, plus A2 e to the 0, which is 1. So we know A1 equals negative A2. So now it simplifies to this equation because they were both equal. We differentiate it in terms of t. So we could use this value that we got. We differentiate it, and we substitute t equals 0 in it, and we get this. So we find A1 to be negative 20.51. So we now have the complete equation. Now what's left is to divide by 3, and this will be our equation. Alright. Practice 9.5. Choose R1 in the circuit so that the response after t equals 0 will be critically damped. Now select R2 to obtain V0 equals 100, then find Vt at t equals 1 millisecond. So first, let's analyze this circuit. We have a current source that turns off after t equals 0, and a switch that closes at t equals 0. Before t equals 0, it's just a current source with a capacitor parallel with these two components, parallel with this resistor. After closing the switch, this node will be the same as this node, because this will be a short circuit. So R2 will be short circuited and no current will pass through it. So and the current source will be open. So it will just be a parallel RLC circuit, as shown in the figure here that I've drawn. So yeah, R2 will be short circuited. It said that we are looking for a value of R1 that makes this circuit critically damped. So for a critically damped circuit, alpha equals omega 0. So we know H1. We square both sides to find R1, and we substitute the value. We find that R1 will be equal half square root of L over C, and substituting L and C, we get that R1 will be 1 kilo ohms. And this is our R1. For part 2, to obtain V0 equals 100 volts, that means that the voltage here will have to be 100 volts at t equals 0. Yeah, so before closing the switch, like just before t equals 0, like at t equals 0 minus, there was a current flowing through this branch. This inductor was considered a short circuit, and this capacitor was considered an open circuit. So there was no current here, there was only current here and here, and obviously they were supplied from the source. So this 0.5 amps supplied these two currents. We can find the current through this R2 branch from the voltage that was given. So if you want the voltage to be 100 here, then the current will be 100 over R2. And the current over here will be 100 over R1. And we know R1 is 1 kilo ohm, right? So 100 volts over 1 kilo ohm is 0.1 amps, right? And we have 0.5 amps, so what's left is 0.4 amps. This is the current flowing here. And we have the current, we have the voltage across this. So we can calculate the resistance. R2 is just the voltage over the current. So 100 over 0.4, which is 250 ohms. And for the last part, find Vt at t equals 1 millisecond. Alright, so we need to find the voltage for this capacitor, or for the whole parallel RLC circuit. So from the values of alpha and omega naught, we know that it is a critically damped response, or because they just told us it is, and we calculated R1 to be for the system to be critically damped. So the response for a critically damped system is in the form of this equation. So we need to find A1 and A2. Now at t equals 0, we know that the voltage was 100 volts. So substituting that in, we can find A1 to be 100, because this is 0 and this is 1. Now we do KCL. We have IC, IL, and IR. We add them together and equate them to 0. IR1 is just voltage divided by R1 plus IL plus IC equals C dV by dt equals 0. Now at t equals 0, the voltage is 100 volts, R1 is given, and the current is 0.4 because it is at t equals 0. This is the current of the inductor. That's because the current in the inductor does not change abruptly, so yeah. Plus 1 micro, which is the capacitance, times dV by dt at t equals 0. We equate that to 0. Then we say that V prime of 0 equals, we just rearrange to find this value. Now, um, we have uh, the equation right here. We need to differentiate it, so I just expanded the brackets so it would be easier for me to expand, and substituting 0 into v prime, because we have this value that we will equate it to, it's just gonna be this form. So yeah, we have a1, so we're looking for a2 now, and a2 will be this value after rearranging. Now we have a1, a2, and we have alpha, so we just substitute the time, which is 1 millisecond, to get this value. Question 9.6. The switch in the circuit has been in the left position for a long time. It is moved to the right at t equals 0. Find dv by dt at t equals 0 plus v at t equals 1 millisecond, t0, the first value of t greater than 0 at which v equals 0. Okay. So we can think of this whole circuit as two circuits at the beginning. Then after the switch closes, or like switches to the other side, this part will be ignored because it is no longer necessary, or like we don't care about it anymore. So at when t is less than 0, as I said, these are like two different circuits, and they have the same ground, obviously. This is just a voltage divider. The capacitor is an open circuit, so the initial, or like VC at t equals 0, is just a voltage division. So 3 right here, 3 times the voltage divider, which is gonna be 2 volts. This is V of 0, and the initial current in the inductor is just 5 over the resistance, because this is gonna be a short circuit. So it's gonna be 10 milliamps. Okay, so we need to find dv by dt at t equals 0 plus. When we close the switch, it's gonna be a parallel RLC circuit. So what we need to do is to find the to find omega 0, to find alpha, to see what sort of a response it is. Is it overdamped, underdamped, critically damped, and then solve for the equation. Okay, so omega 0 here is 50,000 squared. Sorry, it's the square root of 50,000, and alpha is 100. So alpha is smaller, so it's an underdamped response. Since it's an underdamped response, we have to find omega d, which is the square root of omega naught squared minus alpha squared, and it's gonna be 200. So the response for an underdamped system is of this form. It's a cosine and a sine multiplied by an exponential. So all we need to do is we gotta do a KCL at t equals 0 plus for this parallel RLC circuit. So let's add the currents. So IC is C dV by dt, IR is voltage over the resistance, IL is and of course these are at t equals 0 plus. So yeah, and I of 0 plus is 10 milliamps, and this is 2 volts over 500. C is given, so yeah, we need to find V prime of 0 plus, which is what is required. And we find that to be negative 1400. Then we are asked to find the voltage at t equals 1 millisecond. So we have this equation, right? And substituting t equals 0, we know that it's gonna be equal to 2 volts. So sine of 0 is 0, e to the 0 is 1, cosine of 0 is 1, so b1 is gonna be equal to t2. Yeah, so differentiating this this equation of the voltage, we get this long expression, but once we substitute 0 into it, because we have its value, it becomes easier. A lot of things cancel out, so we're only left with this expression, and we equate it to our original number that we found just now. We have b1, which is 2, and we're looking for b2. b2 is gonna be negative 6. And now the voltage at 1 milliseconds is just substituting the time into the equation that we have, so we get this value. And then for part C, we're asked to find t0, right? Which is the first value of t greater than 0 at which v equals 0. So we just equate this whole equation to 0. This term will never go to 0 because it's an exponential. It will never reach 0, so this part of the equation has to be equal to 0. And dividing both sides by cosine, we get tan, and taking the arctan on both sides to find the angle inside. Then rearranging to find t0 is equal to 1.609 milliseconds, and this is our answer. Okay, so practice 9.7. With reference to the circuit shown, find alpha omega naught I of 0 plus di by dt at t equals 0 plus and I at 12 milliseconds. This is a series RLC circuit, so omega naught is the same, but alpha is a bit different. Alpha is R over 2L. So we just substitute directly. We find alpha, we find omega naught. And this part is E. Okay. For part C, we need to find I of 0 plus. Looking at the circuit, this is the current I, and at before t equals 0, this was on, and after t equals 0, it was off. Yeah, so and it had a value of 1 amp. So and basically the capacitor was considered an open circuit, so no current was flowing through this branch. So the only current was flowing this direction, and it was flowing in the inductor. So I of 0 minus is 1 amps, and this is the same as I of 0 plus because it is an inductor. Okay, Now we need to find the I by dt at t equals 0. Alright, so we first need to find the voltage across the capacitor at time 0, and it's just going to be the current times the resistance, which is 100 times 1, which is 100 volts. This is our VC of 0 plus and 0 minus because it's a capacitor. And now we do KVL. We see that VC is equal to VL plus VR. Yeah, and we want to find the derivative of the current I at t equals 0 plus. So at t equals 0 plus, VC of 0 plus, we just found that, and we need to find this quantity over here. The voltage of the resistor is just the current times the resistance, and VL is L di by dt. So rearranging this formula to find I prime of 0 plus, we find that it is going to be equal to 0. So yeah, this is our value. And finally, we need to find the current at 12 milliseconds. Alright, so we found alpha and omega naught, and alpha is less than omega naught, so it's an underdamped response. So we need to find omega d. Omega d is the square root of omega naught squared minus alpha squared, which is 200. I of t will be of this form, and we need to find b1 and b2. We have our initial condition at t equals 0, I of 0 equals 1, right? Substituting that in, we find that b1 equals 1, and we know that the derivative of I at t equals 0 that we just found is gonna be 0, right? Because there is an inductor, so I of 0 plus is gonna be I of 0 because it's an L. Yeah, so we have this value, and we found that to be 0. We differentiate this equation, and we found that it will be equal to this expression. Then we already have b1, we were looking for b2, we rearranged to find b2 to be 0.5. Now all we have to do is substitute the time in the equation, and we find the current. For practice question 9.8, find the expression for IL of t in the circuit valid for t greater than 0 if VC of 0 negative equals 10 volts and IL of 0 negative equal 1. Note, although it is not helpful to apply Thevenin equivalent techniques in this instance, the action of the dependent source links VC and IL such that a first order linear differential equation results. So we don't want to do a Thevenin equivalent technique, but we need to link the VC and IL in such a way through, or like using this current source, this voltage dependent current source. So this question is a bit tricky, so please concentrate. We know that this current IL in the inductor will be the same as the current provided by the current source, but in the opposite direction. So it's going to be a negative sign, and that's what we did here. So IL equals negative 3 VC of t, and we only need to find IL, right? So if we find VC, we can find IL, and we know that VC equals 1 over C times the integral of IC dt, right? That's from I equals C dV by dt, right? Rearranging to find V. And we substitute that in the VC. And we know that IL is the same as IC right here, because they both have the same current flowing in them. So we just substitute that with IL, and we have this equation over here, this inside part. What I did was I took the derivative of both sides, like explicit differentiation, to find in terms of t, to just get rid of the integral. So I have now a first order, this is a first order linear differential ODE. So using the characteristic equation, I found r plus 3 over c equals 0 and r equals minus 3 over c. So, and I know the answer is going to be in this form. This is the solution form. And I know 3 and c, so it's going to be 300t. All what's left here is to find a with the initial condition that we have, which is these two conditions. Okay, so now going back to the original equation that we found, right there, that relates IL and VC at t equals 0 plus VC of 0 plus is going to be 10 volts, right? So 10 times 3 it's going to be 30, and it's going to be negative, and that's the value of IL of 0 plus. So this is going to be like negative 30 amps. But you may notice here that the current in the inductor jumped from 0 to negative 30 amps in 0 time. This is only possible because of the current source. If there was no current source, this would not be possible. So yeah, in this case, because we have a forcing function, this current has to obey this source. So yeah, the current changes abruptly, but the voltage on the capacitor is is smooth because it is not forced by this current source. Alright, so yeah, we found A to be minus 30, and we found this general or unique solution for our problem at for t is greater than 1 than 0. Alright, so question 9.9, let IS be 10 u of minus t minus 20 u of t. This means that for t less than 0, IS is going to be 10 amps. For t greater than 0, IS is going to be negative 20 amps. So we need to find IL of 0 minus. IL of 0 minus is just going to be the current of the source providing it, because this is an open circuit and the inductor is a short circuit, so whatever current is supplied by the source is passing through the inductor. So yeah, it's going to be 10 amps. And VC of 0 plus the voltage of the capacitor is going to be the current times the resistance. So yeah, that's because V of C at t equals 0 minus is equal to V of C at 0 plus, because it's a capacitor. So yeah, it's gonna be 20 times 10. 20 is the resistance and 10 is the current. Now for part C, VR of 0 plus, that's gonna be the voltage of the resistor at 0 plus, which we know the current does not change abruptly over here. So yeah, it's just gonna be the current times the resistance as well, which is also gonna be 200 volts. The current IL at infinity is, it means the current in the inductor with the new current source, the new value for it. So the new one is going to be negative 20, and this is going to be the current in it. Now we need to find the current in the inductor at 0.1 milliseconds. So if you want to draw the graph of the change of IL, we have the value before t equals 0 at 10 amps. Then at infinity it's negative 20, and in that time it decays exponentially, right? So we know it's gonna have an exponential in it. Alright, since this is a series RLC circuit, we need to find alpha and omega naught. Alpha is R over 2L, and it's 10,000. Omega naught is also 10,000. They are equal, which means that this is a critical damping. So IL of t will be of this form: IL at infinity plus some constant A1 plus A2 times t, all times e to the minus alpha t. So IL at infinity is going to be negative 20, we know that, plus these constants times t, e to the alpha t. At t equals 0, we know that the current is 10 at this point. So we need to use this information to find the variables. Substituting t equals 0, this goes away, this is 1. A1 plus negative 20 equals 10. So A1 is 30. This is the equation now. Now we need to find A2. We do this by doing a KVL. We can see that VC here is equal to VR plus VL, right? And we need to do it at t equals 0 because we have initial conditions at this point. V of 0 equals VR of 0 plus VL of 0. So we know this to be 200, and we know this to be 200, so they both cancel out, and VL is equal to 0. And we know VL is L di by dt. So so di by dt, or I prime, at t equals 0 is going to be equal to 0. So finding the derivative of I and making t equals 0, we'll have this this form. Yeah, we just like differentiated this and took t as 0, and we equated to 0 from this part to find a2. We found a2, and then we just substitute the time required in the equation. This is the unique equation, and this is the answer to the question. 9.10 asks, let Vs equals 10 plus 20 U of t volts. Okay, so this means that before t equals 0, Vs equals 10, and after it's 30. And we need to find IL of 0, Vc of 0, IL at its final condition, or like its final state, and IL of 0.1. So IL of 0 here, that's going to be a parallel RLC circuit, right? And IL is just the L is a short circuit, the C is an open circuit initially. So yeah, at time equals 0, the current is just the voltage divided by the resistance. So it is 10 divided by 5, which is 0.2 amps. The voltage at time equals 0 is just the voltage of the source, right? Or yeah, or you could do just like 50 times the current that we just found. So 50 times 0.2, it's the same thing. And now we need to find the current IL at infinity. So yeah, so at infinity we know that Vs is going to be equals to 30. So 30, it's just a new value for the voltage. So 30 divided by 50, which is 0.6 amps. So we could draw a graph for the current IL over time. Initially it was 0.2, then at infinity it is 0.6, and it grows exponentially. So the part D asks us to find the value of the current at 0.1, which is going to be somewhere over here, and we know that it for sure has to be between 0.2 and 0.6. So let's find that. Since this is a parallel RLC circuit, we need to find alpha and omega naught. So yeah, we found those to be 10 and 8. Alpha is greater than omega naught, so it's an overdamped. So we need to find the roots. We found them to be -4 and -16, and we know that the equation will have this form over here. This is 0.6, and we found that. We need to find A1 and A2. We already have S1 and S2. So yeah, what we do is we substitute t equals 0 into this equation. At t equals 0, we know that the current is 0.2, right? So yeah, we find that A1 plus A2 equals negative 0.4. This is our first equation. We need to find another equation, so we find a unique solution for A1 and A2. We do a KVL over here. A KVL as so. Minus Vc equals the current of the inductor plus the current, the voltage of the inductor plus the voltage of the capacitor. At t equals 0 plus, that's going to be 30 equals, that's going to be L di by dt at t equals 0 plus Vc of 0 plus, which is 10 Now we rearrange to find this uh, this quantity that we want, and it is 1.28. And we substitute. We first differentiate the equation of IL, and we substitute 0 plus in it so that we get this equation number 2, and we solve them simultaneously on your calculator or by hand, whatever suits you. And we get that A1 and A2 equal these values. So we now have our unique solution, and all what's left is to substitute the value of t equals 0.1 seconds into our equation, and we find the current. And thank you so much.